Okay, hello. Just staying on. Got a little bit busy there, but should be good to go now. Let me go ahead and reveal myself. Howdy, howdy, howdy. How's everybody doing? I have a cool update about my project here, because I got some mail and it came in just on time. I essentially got, oh, hold on, we gotta turn on the circuit cam. Oh, there we go. I got a new piece for the STM32 board. I got a new crystal to put on the board so that way I can have an accurate clock. Because a few streams ago, I tried to make a Rust project that did a delay of about 200 milliseconds, and it had a 2 millisecond error on it, plus or minus, which is really bad. You don't want that. Things can be way more accurate than that. And for music and DSP stuff, and probably robotics too, you would want something that's a lot more precise, or rather not precise, but accurate. So they recommended buying an external crystal to put on this. And that is probably what I'll be doing for a little bit of the stream, because this thing, it's just not it. It needs to have that crystal. So unfortunately, I'm gonna have to unplug my stuff and get some soldering tools out, because this thing is really tiny and you can't put a soldering iron to it. I do have a trick though, but if you look at this board, hold on, where's it at? Okay, it's gonna be hard to see as usual. I'm trying to see if the camera will go into focus. Ooh. Looks like you either have to get real close to it. Let's see, will that make it go in focus? It looks like it's trying to go into focus. I'm trying to be as stable as I can, but it's not really changing. Oh well, fixed focus. If I'm not mistaken, yeah, right here is a bunch of dots. It's probably not going to show up, but there's some tiny sod pads there. I'm gonna have to put the thing onto that. Now let me go get my part real quick. One sec. Okay, so I found the part. I got it from DigiKey. It is a, as you see, crystal, 16 megahertz, and we need to get this piece out. So I ordered a reel of 10 of them because I figured I might be using multiple of them, and also if I sneezed, I'd lose them. Okay, if you haven't looked at parts before, those little gray things, those are the crystals. They're about the same size, for reference, as a breadboard hole, which means they're tiny, super tiny. Like, there's nothing outside of the world of electronics that really can compare in size. This would be a crumb. This is 10 crumbs right here. And they can get lost really easily. And you also need to have the right tools to do the job. I may have the right tools, but what I need to make sure is that they match in size, which it, again, hard to see on camera, but it does. In fact, why don't I move this over slightly? There we go. But just from eyeballing it, this basically matches up, so I should be able to get it done. It's just I don't know how well soldering it on will be, I'm a little bit worried. Because essentially I need to heat this up to high temp and slide it on. I don't have a microscope, which makes it even more hard. But I do need another tool, so I'll be right back. Okay, I got two different tools here that could maybe work. The first one being a mini hot plate, super tiny. Essentially, it's a mini, yeah, maybe not an oven necessarily, but a pan. Think of a frying pan. The top of this is a pan. So it has a component that makes this top part very, very hot. And you put your circuit board on it like this, and it heats it up from underneath, so that way you can hopefully move the soldering around. The problem is, I don't know if I'll accidentally be heating these bottom components. I'm a little bit worried that that exact fear is what would happen. So this may not work because of these being on the bottom. These are all resistors. These black dots, these are all resistors. If I look about how it lines up, this dot is a reference point, and there's definitely stuff all around that. So that's unfortunate. This means that we will have to try to do the hand soldered way. But like, look at this thing. It's super tiny and cute. See that? It's super tiny. If you ever want to get something that heats up a very particular part of a pan, not a pan, but a PCB, that can do the job. I haven't personally done it, but I've seen a friend do it, and it worked really well. The other thing, also from a friend, this tiny little USB powered portable soldering iron. This is the TS880P smart soldering iron, and this thing is at least online regarded pretty goated. You're able to swap out the tops using this connector. You just buy a few different tops that have different tips. It comes default with this really small one, which is what I need for this exact use case. But I'm curious if this thing has any charge. Yeah, it doesn't, which is fine. But this is what I will be using to charge. It comes with a USB-C, and it allows you to just, you know, go with the flow, go out into the public domain with a portable soldering iron. It can come in handy when you're doing robotics for sure. But I'll need to charge this before we can actually put on the thing. So let me do that. I luckily have a cable. Comes with it, or at least it came with this one. That's fine. The same cable can work. Oh, it's USB to USB-C. We'll do a different cable. I will remove this for the meantime and go plug this in real quick. But yeah, just wanted to show off some cool gadgets that I got. I would love to be able to use this. I have yet to have the project though that needed it. Just got it because it's always fun to find new cool gizmos. Okay. Let me go plug this in. I'll be right back. I have something here that is going to be very loud if I turn it on. But I have a fume extractor that I will be using most likely to actually make sure I don't breathe any of this toxic stuff. Because why would you want to breathe toxic stuff when you could do that with League or Dota or some other video game instead? If I quit those games, why would I just transition to something else that has toxicity? Let's see how loud this thing is when I turn it on. That's not that loud. It's more like a vacuum cleaner. But you see? Nice little hose if you ever seen the Teletubbies. We got a nice little vacuum. Just like that little guy from Teletubbies. Using that. I don't think I'm gonna have too much solder for it, so I'm probably okay, but you never know. Having trouble trying to see if this soldering iron is battery powered or not, because I thought it was. I need to bust out the... Oh, it doesn't come with the manual. Debated. I think it's just powered off of USB-C, which is fine. It makes more sense that it would be battery powered. Pretty small. Found the instructions, never mind. Let's see what it says. Soldering tip. Button A. Just real quick. It's definitely not going to come up on stream, but I'll say what it says. So there's some firmware I can download off of a website. Then okay, then it starts talking about different buttons that exist on it. It has two buttons, button A and B. That's it, actually. It doesn't go into any further detail. Oh, hold on. What's this? Heating. Takes 30 watts. Okay. So you gotta let it heat up. But it doesn't say anything about battery powered. So it definitely uses USB-C. And don't plug it into your, USB extender, because that's gonna be too low power. It takes 30 watts. 3 watts power. So you have to make sure that you are supplying enough power. I also realize I don't actually have a stand for this thing. I don't really have a place for this to sit when it gets hot. I mean, I can set it down like this, I guess. But what's stopping it from rolling off the table? I guess that's this screw. The screw is stopping it. Yeah, I should really get a stand, but if it's like this, that's fine. I just gotta try really hard not to drop it. We'll see how that goes. All right, 30 watts of power. How much is this thing? Doesn't look like 30 watts. I might need a different. Pretty sure I'm gonna need a different cable. I'll be right back. Okay, let's hope that this cable is long enough to power this and use, because I need to use a USB-C, a power delivery cable, to make it work. Something tells me it's not going to be long enough. Oh, not even close. Okay, this is a interesting cable. Hmm. Yeah, it's too short. I might have another cable. Most of them are pretty short. I think I need to just make the outlet be closer to me. There's two routes. I get closer to the outlet, or the outlet gets closer to me. I think the second one is going to make more sense here. Fit even? Should. Yeah, it fits. Okay. I think it's because I had an external battery pack. I think this might be the solution. Having this battery pack instead. Not sponsored by Anchor, by the way. Just happen to have a lot of their products. Okay. Let's try to do some wire management. So, my theory is I take this. Okay. This was not wireless before, or battery powered before, but we're going to make it battery powered by doing this. Oh yeah. Battery powered. Love to see it. Okay, so let's get all our things ready before we start heating stuff up. In fact, I might move this to over here. So that way it's just not in the way completely. I'm going to need... Oh, what the heck? Why'd the music stop? I'm going to need... Hold on. I'm trying to find my mouse right now. There we go. That's pretty dumb. Why does the music just stop randomly? Oh, I reached the end of the playlist. That only had 10 songs. No wonder. Makes a lot of sense. Alright, we're just going to put on the popular. We'll see what this music produces. Okay. So, I'm going to turn on heating. Oh, shoot. It's getting hot fast. Well. I didn't really clean the tip or anything, but... As you can see there. That's hot, boy. That's 300C already. In that instant. That was super fast. That was super, super fast. We gotta be very careful not to burn ourselves. If you never soldered before, this shit is hot. Okay, good. It's not spilling out. So we got these here. I need to extract one of them and hold it with a pair of tweezers. Tweezers. Oh, I can tell it's getting hot. It's changing color. Let me double check the data sheet on this guy to make sure that the pin that I'm looking at is the one we need to solder. Oh shit. Oh, the cable's moving. Okay. That soldering iron. Yeah, I can move my mic. That soldering iron is a USB-C powered soldering iron. It's called the what is it? TS80P. That's what this iron is. And it's super portable. If you have an external power bank like I do, it's essentially battery powered. But without it, it's not battery powered. Adobe. And then let's open up this data sheet, which I'll show real quick. Okay, so we're looking for HSE, which stands for, no, sorry, not HSE. Wait, actually, high speed external oscilloscope or oscillator. So it's HSE. We've been normally using HSI, which is internal, which is what they describe here. But HSE, they are saying that depends on which one I have. Oh shoot, did I blunder here? Did I need? Hold on. To help select the crystal and its associated capacitors. Okay, never mind. There's no capacitors on it. I did not buy capacitors. We may have to take an audible here and do that another stream. I'm gonna go ahead and turn off the Oh, I don't want to increase it. No, no, no. I think I just let go. Yeah, I think I just need to unplug it and then just let it cool off. Alright, I got a little bit ahead of myself, but I didn't actually have pieces I needed. A little bit of a bummer, but that's okay. We can do something else. Essentially, I'm going to need to buy some capacitors, which they have in this data sheet. I think the reason that I didn't buy capacitors is because I hyper-focused on this statement. We're talking about the actual crystal, which I did buy, but yeah, you're going to need capacitors. That makes sense. On circuits I've laid out before, you have to have some capacitors to filter some unwanted ringing out of the chip or out of the crystal. Okay. No big deal. Apparently you can have it. Oh, if you wanted to do it to actual pins, I see. I see. Well, I definitely don't have breakout capacitors either. I think. Let me check. I may have one. Hold on. Because if I have that, that changes things too. Oh. A little bit for nothing, but we got to see a little bit of a show and tell, I suppose. See how hot is this thing? Not radiating heat, but I don't really trust that, so I'm putting it over there. Let's clean up the workbench a little bit. This battery will be used for next time. We'll take this and put that there. So I grabbed a few things because we are going to put some buttons on our board. Even though I had buttons built in already, I don't like how they're wired. They're not in a place that I like. So instead we're going to put some buttons on our breadboard. Gotta make sure I don't lose these crystals too. That's important. Okay. Okay, it's a little warm. But nothing that's too bad. I'm gonna... Like, I could hold it with my hand. Yeah, it's pretty cool, actually, by now. Dang. That's efficient. It's really efficient. Put it back in the box. And I can just store it away for later. Except you gotta grab the right piece. Come on. Okay, how about this? We take this out. And we pull it out from this way. Then it'll come out. There you go. There's the soldering iron. Yeah, I didn't see it before. Okay. Do we make more wires? Breadboard wires. I think we do. So I'm gonna put this back to where I usually keep it. Right there. Right in the frame. Yep, there we go. This goes over here. This goes over here. Try to make it a little neat. So, which way? Yeah, it was this way. So we want to put a couple buttons on it because remember this is a chess timer after all. And we want ways to control it. So we got this little kit with some random pieces here. Got some trim pots, some capacitors, photoresistors, tilt switchers, capacitors again. But we want this button. It's a pretty cheap button. Pretty cheap button, but there we go. But it will certainly do the job for what we're trying to do. So in the ideal case, we probably put a button on each side of the breadboard because this is supposed to be a chess timer. So you click it on one side and click it on the other side. And I think we go off of that. Yeah. Whenever you have these push buttons and you have a breadboard, you have to put it in that position. Otherwise, it just shorts itself. So I'm gonna put one there. I'm gonna put one here. Nice part is we can pull off of the rail to get a 5-volt supply. And we just gotta get a wire going from here all the way to over here. Which in this configuration may not be as easy, but I probably will just run a wire that goes along the bottom here and off to the side. And then a different wire that goes, or we could do it across the middle. That could work. We don't really need these debugging probes anymore because we proved that the 7th segment worked on its own. So I'm gonna get these out of the way, make it a little bit neater. I do, however, need to plug in these wires. Which I don't really have a good memorization of how they're exactly plugged in. Let's see if we can jog our memory by looking at our data sheet though. If I recall. There we go. I'm like, the layout seems different. Okay, so SCK goes to D13. We did MOSI, CS. That's it, and ground. So we can hook these in. And also make sure this thing works when we turn it on too. SCK, this clock, this is chip select, this data, and this is clock right here. Oh, this isn't the right view. We need the one with the circuit, lol. See the top. Data in is master out. D11 means D10 is our chip select. Okay, if everything is good, I can just do this and then do the reset. All right, cool. F's are bad. We have F's. We got buttons that don't do anything. So one thing we may need is a resistor. I think we might not need that resistor though, because we got to do a pull-up circuit configuration. We need to get the circuit to hook up directly with this. I'll get my tablet here. I'm gonna get the drawing mode out. Okay, we want new page for button layout, or rather, yeah, user buttons. Okay, so we got our STM. Ooh. Hold on. Okay, there we go. We got our MCU here. Ooh. Things dying a little bit. Your way can give it power. We'll let it work for now. Okay, we got an MCU here, and we're gonna have 2 pins. One of them we're just gonna call input. Actually, how about I do this? Oops, a little too far. Okay, MCU, not Marvel Cinematic Universe, but microcontroller unit. We're gonna have D1, which stands for digital input 1. We have digital input 2, and then we're gonna have ground, which will just be set to ground. We're gonna have 5 volts going to our button that acts like this. Okay. Now, if we weren't careful, we could put the MCU in an unsafe state where 5 volts end up going through the circuit too fast, too much for our pins to handle, because there needs to be some kind of resistor to control current. Otherwise, you could have infinite current, and current is very damaging to these devices. Same with voltage. I mean, they're rated for both, but current, you usually have to do something manually. So I got those resistors over there to make it so we can control how much, oh, I didn't change my color, how much electrons flow through this. Thinking about it though, I may not actually need those resistors. That would be the naive way to do it. I think the proper way is these pins, D1, inside of it, you can configure a pull down resistor to ground. And this is what actually you look at. E1's connected here, but inside of the MCU, you can configure an internal pull down resistors. That way, when you do this switch thing, you have 5 volts here. When it's open, there's 0 volts here because this has no current flowing through it. So you got 0 volts, 0 volts. But as soon as you connect the switch, like so, as soon as you connect the switch, then you have 5 volts here, but the extra current goes down here, and you don't have to worry about it being an impossible situation that has current that the MCU can't handle. So let's check out our code and see if we can configure pull down resistors with this library. We're looking for this. Open this. code. Okay. Okay. So, first things first, we can... Oh, okay, we don't actually have that LED anymore, but we can make a new instance. Let's do it below... Thinking we do it here. No, we'll do it below the pack. So we're gonna say initialize, or rather create user buttons. And the way you do that in here is we're gonna do input, new, and you can see it defaults to a pin and a pole direction. The pole direction is that resistor I was talking about. We want to pull down. But first, let's find a pin that makes sense. Ideally, I want it to be on a similar part of the board, so that way we can have wires go in the same area. So, I think we can just do... below it or above it? Ah, here we go. I think it's gonna be one of these. So I believe you can configure any of these to be digital input output. So we're gonna do D2. G2 and G4. We'll do that because it's just dedicated IO, meaning they don't have any other circuits attached to it. IO stands for input output, by the way. So D2 will be PF15, which we can just type in here. PF15. And then the pole, we want pulled down. That's how we get that circuit we drew earlier. And we're going to say this is equal to, oh, we need to say pack, by the way, because it needs to know what library or crate to get this PF15 from. Okay. We're going to do let mute. Well, we'll just start with let. IO is a Dota support. I think you're thinking of, was it Wisp? Wisp is IO. But yes, IO, that's true. IO is feeding in my fountain right now. What the heck am I? Okay, we're gonna say white button because it's chess, so we're going to add some names to it. We're gonna do let black button for the other one. Input new. Oh shoot, what the heck? It was doing some wacky stuff there. Okay, PF15 was the first one and PF14 is the other one. Wow, look, they're similar. PF14 we're all pulled down again. Oops, that's too much. All right, we created our two buttons. Because we're not using them right now, we'll do an underscore so that the Rust compiler doesn't yell about unused variables right now. But simply a placeholder. Okay. This white button and black button. In terms of our loop, we want it to take our input. Now, there's a trick that you have to do with buttons because they bounce. Do we want to get into that now, or do we want to do wiring? I think I want to wire it first. That way it's easier to debug. So let's go to the circuit cam. I'll show you how I wire this thing usually. We're going to take out power for that, just so we don't short anything. And we need to figure out a way to get power from the rail to this button, and then from the button all the way to over here. So we got some tools. This will be our stripper. This will be our cutter. This will be our bender. That's your cast for tonight. We got our wires here. Since we're doing power, we're gonna use red. Makes sense, right? I feel like we don't need a lot because it's just going from here to here. So it's gonna be relatively quick. What I do first is I pull some of this out. I then take my stripping tool, I stick the wire in, and then I just pull, and then it takes out that insulating layer. I take my bending tool, I bend. Very nice. So then I come over to the breadboard and I have to do some measuring. So since I'm going straight to this button, I'm going to do power from here. I'm going to measure how many holes I need. Since I just need to go in the same row, because that's how breadboards work, I don't need to go all the way down to here, but I can just make a wire that's this short. I'm going to take that length and then add 2 more holes to it, because we need to cut off some wire to bend. I'm going to take 1, 2, 3, and I'm going to hold my finger there and try to do snip snip. But I need to do it with my left hand because I can't cut with my right hand. I coordinated, or sorry, the other way around, but yeah. Okay. Now because this thing is so small, I may not be able to use my stripping tool. Yeah, that's way too small. So I need to use instead the hand tool that you just got to pull with. Now I'm not really good at this, so it's gonna look like I'm struggling a lot more than probably somebody who's been doing this for 50 years. That's all right. So I think about, let's see, we need to go about here. About here. About here. So I'm just gonna take my tool, put it in, and bend and pull away that insulating layer. This thing is configured for the exact gauge, wire gauge I'm using, so it's a lot easier to just pull off. If you did it at too big of a gauge, it just slipped right through. If you did it too small, it'd cut through. You need to have the right amount. I bent with my fingers there, but you probably should just use a tool. It's a lot easier. Okay. Then just get one side in. But these smaller sizes is a little bit more difficult. Gosh. Get one side there. We might have cut, or we might have grabbed too long of a wire, which is fine. We can work with that, which means we're not completely on the edge. But geez, you can really see I'm struggling to get it in there. Ugh. Getting a little twisted up too. Maybe what I'll do is straighten out one side and use the leverage I have to plug that in. Hopefully I don't break the wire doing it. Okay, so that's in. Now we bend it down into place. Kind of force it in a little bit. There we go. Yeah, that must be the way to do it. So luckily, because we already bridged the gap, we can do another small wire. Just come straight into this. So do a similar thing. Take our tool. Grip one end. Super easy with that tool. It's amazing. Measure it out. Well, bend it, then measure it out. Come on. Okay. We're gonna do to about there. Take this out. Snip it. Grab our wire. And kind of just eyeballing it this time. Feel like I'll make it work regardless of the size. Doesn't have to be exactly perfect. Just gotta make sure we have a wire really. As long as we got the wire, we're in a good spot. Okay, so like we did last time, since I learned, we're just gonna keep one side flat before bending it. We stick it into the rail, and then we drop it down into one of these holes. I'm gonna try for the closer one this time. Maybe I should use this tool. Maybe this would help. You know, keep it steady. And also to like flatten it in. Yeah, that's the way I should have done it. Use your needle nose pliers to force it in. Okay, the small ones, those aren't fun. Big ones are much more fun because they're straightforward and they fit. You get to use the nice tools. Alrighty. Yeah, I'm thinking what I will do is route the signal here and have a separate signal coming off so I can have these flimsy ones that I don't need to cut, because we want this to have some flexibility, and I have some pre-cut ones that are relatively long that I like using. So let's do that. In fact, I could route this in a way where I have these signals coming down and they both end up here. Maybe that'd be cleaner. So what we'll do is we'll make one white, one black. That way we can actually, you know, treat it to the code. Make it reflect the code. So, at the end, we're going to stick it into the hole. Actually, we decided, yeah, I'll go on the bottom because now I just realized that the rail is, I can't use this side, I have to use the bottom side. So luckily, it kind of just rides along the bottom pretty easily. We're gonna route it up around the clock. So that way, if we put some circuitry here, we're not making wires go over that. Get a little more slack in the wire here. And then we're gonna have it travel above the rail for the same reason. Oh, wait, no. We're not gonna do that actually. We're going to tie it to about here. We want it to sit probably in this row, thinking about it, because we want the black wire to end up right around here. This whole side of the board is used up by that IC, so I guess we'll just do it. We have this white cable coming here, and then the black one's just like one slot over. So because this is so long, We're gonna kind of just eyeball it again. How much slack we need. I think that's about good. I may have made this a little too long, but it'll work. Nice tool. See how much faster that is? Nice little tool to cut that up. And then we need to bend to the end. There we go. That just fits in there nicely. Yeah, it's got a little more slack than I'd like, but it'll work. Okay, let's get the black wire now. This one I usually use for ground, but in this case, we're going to say it's otherwise. Black signal. We're going to put it here. And we're going to route it to kind of go over all this. Maybe here is better. It kind of ties down these wires a little bit. It's gonna... Better yet, I could weave it underneath. How about we do that? We're gonna weave underneath these data signals. Or these, yeah, these are data signals. Because it's neater looking. Put it in the row. Come on. There we go. So this wire exists. It's coming along the breadboard. And we want it to go kind of similar distance. We'll cut it to 1. But because we want it to be on a different row, we need it to be a little bit shorter. So I'm going to measure it for 1. But expect it to connect in a different spot. Let's see how this turns out. It's definitely shorter, I could tell immediately. In fact, you could probably make it go further down. So that way it's more distinct that it's a different signal. Yeah, with these long ones, you have so much flexibility. In fact, I might even just tuck it underneath the white one. Just like so. Pretty simple. So then we come to... Oh, I took it off my desk, I just remembered. Okay, well, I'm gonna get probably a blue wire. Should I make one? I could just make one. Yeah, maybe I'll just make one. Let me do that. Make a black and a white wire. I was thinking I didn't want to waste these, but I think for this kind of signal, it would help. Kind of do an eyeball on this one since it's such a non-official cable. We're gonna do it to like, we'll just cut to like here. That. It's definitely a little bit longer than I needed, but it's fine. But I do need to figure out where PF14 is. is D4, which I think is here, yeah. Okay. Let me look at my code. I put white as PF15, so PF15 is actually B2. What language is this? Is it English? I don't think it is. I mean, I'm hearing a lot of English words, but it gives off K-pop vibes. Yeah, I guess it is just English. I'm so used to that build-up being in Korean that threw me off. Oh, look at that, we got the wire to hold itself. I don't know, this is just free music, so not free, but they're calling it pop. It's saying "Way You Make Me Feel" by Adeline Pike. Yeah, it's not gonna be any mainstream music, that's for sure. Gonna eyeball it again. Okay. Now we got all our wires. There's so many of these little insulated things. Now we got hip hop. Used to be left on red, now all the girls go holler. Now all the girls go follow. All the fake fans gon' pile up. I need peace to borrow, get that shit right back tomorrow. Somehow all the fans go bravo. Okay, we got our signals. Hopefully I, oh shit. Shit. I was hitting those buttons with nothing configured. That code was not on there yet. Hopefully I didn't just like fly it. I think it was instantaneous, it's not a big deal, but you gotta be careful not to fry these pins. Usually they don't handle a lot of current. I'm crazy. But not really. It's a tiny trace. I think the Arduino Atmega 328P is a like 20 milliamps. So what we'll do is probably make a program that just prints the log what values it thinks each of the pins are at. Just tightening up my wires because we pulled it way out of this box. There's so much variety in this popular playlist. Holy crap. It's jumping all over the place. It's going from K-pop to hip-hop rap, whatever you want to call it, to this upbeat generic guitar. I'll just throw on some electric music. Yeah, that'll answer the question. It's just one genre. Oh my gosh. Weird. Alright. This guy. No, actually code. Not that circuit board yet. So right now it's just looping this right. We're just gonna do an info where we do. Oh, I actually don't know how you can pass in values. I haven't experimented with that. Can I do that? Ideally, I do something like function to read. So if I were to do, I probably have to make this mutable. Oh wait, not the API. I probably need to make the button mutable. Let's see, how do we read input? If we go white button dot get level, what does this return? This returns a level. Can I put this inside of my macro, info macro? Does that work? I don't know if it's gonna like that. Okay, it's not complaining, so maybe it's fine. Oh, now it is complaining. Expected string literal. Yeah, okay, that's what I was expecting. Info is a part of this D format. What if I did different type? Do they have different types? We can do right. Right might be what we want. Info might just be strings. Although this kind of looks similar. Oh, hold on, args. So I can pass in. Maybe I can pass in what you do in C. Well, this is an item. Bit flag, timestamp. This one takes one args, whereas that one was like a stream. Trace print line. New line, rather. Function like print ln. Function like int. I see. They made a bunch of similar named functions as in other libraries. They even have a certs. Wow. They can do testing. Format. Is there a data sheet for this? Because maybe that would make it easier. Not data sheet, documentation. Let me try and open up a new window here. We're gonna look up crates.io. And then we go to DFM and D format, I think it's that. DFMD. Yeah. Okay, come here. Documentation. Okay, efficient logging. That's perfect. Always log data irrespective of log level. Data at info level, which is what we want, because there's different levels you can do with debugging. You can have different messages that have different warning levels. So in our case, we just want info because there's no warning to be had. There's no error to be had. Writes formatted data to the formatter. I feel like this write might be a key thing. What do we got here? Type to feed debug values into deformat macros. Encode raw deformat frames. Formats to handle this string. An intern string created via intern formats. Oh, here we go. They have an example. Animal implementation can make use of the. Actually, how about we go to println? That has nothing. Wait, what's this? Refer to the manual for this syntax. Okay, cool. This is what we wanted. Format book. Not hints. Not bit fields. We want a bool. Booleans are this. So they made it look like printf. It looks like. So if we did info, we could just pass it in like we expect. So info, do this, where we have, let's see, white button. It's like this is the keyword. Cool. Like that. There we go. Oh, okay. Oh, no, delicate. It's faking me out. Expected reference bool with found level. Okay, so I just need to convert level into bool somehow. What's a good way we could do that? Go to level. This is enumeration. From bool for level. I think if I go dot from, oh no, that's format though, dot fmt, and that's not quite what I wanted. What happens if I go here? It returns this function, which returns this. Get current pin input level, returns level. How can we convert level into bool? What is the Rust way of doing that? So this error originates in the macro inf. Was a function. First of all, did I write this right? Yeah, I did. Let's see. Rust convert. What Rust equivalent of typecast, I guess. As. Oh, okay. So we do this as. Cool. Does that work? Cannot cast this into bool. Dang. So then it has to be something that's library that I can do. Oops, too much. Get level. Go to level. So level itself, just brand new enumeration, has low and high. These are the values. And oh, am I using the format in this? What was this? This is for, yeah, I am. It's right there. So I think I can just format it. Derived format, if I'm using this, I can do what? DFMT? Does that work? Or can I do format? Will that work? Format. Can I try bool? I actually don't know this function. What's this function? didn't give me anything. It just showed me level, and then that showed me level again. All right. Get level. Actually, what we should do is check. See if there's an example that uses this. From what I've noticed, the majority of the examples exist in the NRF branch. And what I mean by that is I go to examples, and then I go to NRF here, and then what is this? This is just saying button pressed, button pressed, button pressed. Not quite what I'm looking for. What would be something that might have a timer, perhaps? This is unwrap. Something that prints something besides a string. And part of me is wondering if they've even done that before. Reading, writing. They don't actually write it out on the log. Wrote hello and UART. Maybe because you're not usually supposed to. Unstructured, brain dump, push notes, optimization goal. No, not quite what I'm looking for. That always prints the content. Okay, how about print ln? Maybe that's what I need. Print ln. And then I just give it this. No, do I like that? Can I find the macro? Do I need to pass it in? I do. We'll just pass everything from that library in. Okay, what do we got here? Expected string literal. So it did happen. So if I do this. Oh wait, what am I doing? I think I just need to do this. White button. And then we do equals level. Whatever the name of the data type is, isn't that? Will that work? Unidentified. It's no levels. Okay, if I put bool. Invalid type. Is it lowercase? It is lowercase. I need this whole name. Embassy. Is it STM32? Is that it? That's underscore. Well, hold on. Is that level? Oh no, it's not important. Let me see. STM32 GPIO level. Do you do that? Ampersand. Nope, that doesn't work. Worth a try. There has to be some kind of function I need to do to convert this from Boolean to, what was that? Oh yeah, Boolean. Oh, maybe I just leave it blank. Oh, that is what I do. Okay. So if I do info, this will print it out. Yeah, I guess. Shoot. We'll just do that. And we'll make one for black button too. Okay. Oh, we need to actually call the black button. Okay, let's build this. Cargo build. Doesn't need readable. Guess that makes sense. We're not actually changing anything. We're just reading it. Yeah, that makes a lot of sense. Core format. I imported something that we're not using. Alright, cool. Then we'll do run, cargo run. So high. The button's high right now. If I do this, that doesn't change anything. Interesting. It's high. What if I take this out? It's being held up high. Do I misunderstand how this button should be connected? Perhaps my button needs to be on the same side rather than across the valley. Maybe this is shorting it across the valley. Maybe I need to be here. That's always possible on this. So let's undo these for now. And we'll just connect it this way instead. For a quick trial, we can do it, I think, like this, and just see how that may affect it. Okay, one's high, one's low. Ah, there we go. Yeah. So across here, they're the same. So you have to do it across the different rows. This is the same row. This is 2 rows across. So when you press this button, it's actually shorting one leg to the other leg on the same side. So I hooked up the white wire on the bottom here, which is fine for our wiring on this side, which means on this side I have to do, I gotta stretch a little more. That's fine. Yeah, that should be okay. So I'm going to go over to my code now. Okay, you can see it spamming. The bottom one is the white one, the top one's the black one. I'm going to hold it down and I'm going to hit Control C on it so we can pause it. And by the end of it, the white one was being held high because I was shorting the circuit. Black one was still low. We run this again. That's how we reconnect. They're all lows right now. I press a button. You can kind of see it. The black one goes high. If I do both at the same time, everything's high. They're reactive. Now, to the naked eye, this seems fine. But if you were to put a signal on it, it is going to bounce. And that's what we'll do. I'm going to put a logic analyzer on it. Or actually we'll put a scope on it. So for the scope, need some special probes. Which I have right here. Let's do it on one though, save time. So we hook up our oscilloscope here. We're gonna have one wire on ground and one wire on the button. So I'll hook this up to ground. Let's do it here. Or actually we could do it. Yeah, we'll do it here. Ground, and then we'll hook it right here. Because this is a cross. Oops. This is across the button. So now if I start the oscilloscope, you can see it's reading a signal and then it jumps up. Okay, how can we make this a little bit easier to see? We want to zoom it out. That's how we do it. With more divisions though. You see that? Hold on. Okay, this is me pressing it. Let's see, is it any instantaneous? Oh wow, it's relatively smooth. That's pretty impressive. It went from low up to the top. I was not expecting that. Maybe it smoothed it out though. Maybe there's some noise here that smoothed out. I'm gonna bring the buffer down. What is this level? This level just moves it. We'll actually use this. Ooh, okay, there we go. Now we can see the noise. That's what I'm looking for. Ooh, it's centered too. It's repeated. Offset. It's just 0 offset. What the heck is it? 5 volt offset? No. 1 volt offset? No. 0 volt offset. Run. Can we turn off channel 2? Maybe not. Continuation, sample mode. I'm learning some stuff. Bear with me. The position of the time. We do want it to be behind. Ooh. Okay. How can I fix the scaling? That's what I really want. Time is XY. It should be vertical scaling. So it should be this. Range. Here we go. Do a volt division. Oh, did you see that? See that noise? And then we'll do shift. This is me pressing the buttons relatively smooth. I wonder if it's built-in circuit to debalance it. 'Cause I'm actually pretty impressed. If I were to zoom in on that, that's a solid signal. How can I make this better? That shows me the top of it. Let me zoom in. Maybe we have a trigger on the rising edge. Single. Yeah, it's actually not so bad. Never mind. Hysteresis. That might be it. 0 volt. Hold on. Okay, this is some of the noise I was looking for, but even that, I think this is hysteresis. Oh, okay. That one had some bouncing. Uh-oh. There we go. I just gotta use these smaller divisions at 0 seconds, ideally. Samples? We want as many samples as we can. We want to capture those gross moments. Single. Position. Back to 0. Single. Okay, there we go. Well, it's the same bounce. I'm surprised what's going on here. I was really expecting this to not have any reaction. But it's doing something to the actual probe pins up here. Well, normally you're supposed to build a debouncing. Some debouncing logic into any of your GPIO. I wonder if this has that built in. I would like to think it doesn't, because not everything's button. If I go to input, or actually I'm gonna go to this function. I mean, it shouldn't, it just says get level. How does it get level? It goes to level, and it checks if it's high, which checks if it's low, which checks the data register, input data register. So I was just looking at the register for the STM chip. Nothing with debouncing. This is where we go into the STM chip and see if there's anything that they mention about signal being wonky. Maybe not this data sheet, but one of these other ones. That's the Prusa. That's not what I want. Go to home. Maybe here. I go to general purpose IO. Be down around here somewhere. GPIO. And then maybe we check out the floating, the input states. Actually, let's search for the word bounce. Bounce happens twice. And this is in a tamper backup register, which I'm not using, and a UC power delivery. Hello, sir. AFAC, how's it going? How do you do? So this is for USB-C. That's not relevant to our circuit. Okay, maybe we don't make any debounce logic. I was thinking maybe I needed it, but it might be fine. Because these buttons, they are responding pretty easily. And when I did the oscilloscope, it looked pretty fine. Yeah. Okay. Let's get into the fun stuff. How about we make some conditional logic based around these? We're going to stop that program. We need to make it so, at least for now, let's divide it into 2 different segments. When I press the white button, we turn this one to all Fs. And when we press the black one, we turn the other one to all Fs. So let's try doing some toggling. How about that? That would be the better way to do it. So we're in this loop, right? And we are going to have 2 different versions. One of these versions is going to be writing the hex, the value, we'll just do 000FFFF, or let's just do ones, while the other one will be 1111000. Unwrap both of them. We need to have some logic based off of these levels. We're going to create one mutable variable, let mute. We're going to say turn state. Which we're going to define as bool. And we're going to initialize it to false. We're going to start that. False is going to be our white turn. Okay, switch. So we'll do turn state if turn state is equal to true. Then we want to display, we'll say this one. And otherwise, we'll display this one. Actually, that's not what we'll do. If this is true, we do that. Otherwise, we display this one. Never mind. This is right. Okay. And we need to do some logic. Do some logic that toggles the turn state based on which one was just pressed. So we saw from these two functions we could just do the get level to get the general level, but we probably want to do it when it's high. So we'll do some logic such as if white button why is it not, hold on, something's off here. It's not auto completing here. White button is high. What is it complaining about? Syntax error. What's the syntax error? Syntax error, I mean, it's not going to work. I see that. We want to do turn state equal to true. If black button is high. You know, my keyboard's dying. Battery wise. Turn state should be false. What is it complaining about? Unnecessary parentheses. Really? Is that how you do it in Rust? I guess so. Used to see. Okay. To me, this should work. So I'm gonna also put this function. Oh, that's not what I wanted. Shoot. Went too far back. Went way too far back. Okay. To do this again. Turn state is equal to true. And do single thing. Yoink it. Paste it. It's on new line. Place this with black. And set this to false. Then we will yoink this line, non-comment it. Yoink this line. Oh jeez. Too much. Okay. Yoink this line. Insert it here. Okay, there we go. Let's guard run this. Hold on, something was not right. Failed to parse IDs. Oh, okay. So you can see we're driving ones right now. And then we press the button and it was all ones on this side. So now we have a game of chess, but there seems to be an error with not displaying the other thing. I think this is because it's hex. It's trying to just display the number. It's trying to be smart. This library is trying to be smart. We might need a different function. How can we do this? That's interesting that it would do that automatically. It's trying to save energy. Yelling at me again about the parentheses. How about we do my display dot right? Raw? Yeah, raw. Let's do raw instead of hex. This should fix the problem. Right raw. Okay, that's not used right raw. Expects this. Oh, that's not gonna work either because it's going to make it a different thing. Okay, how about right string? Will this work? If I do this. Method takes 3 arguments, but 2 were supplied. What is the right string takes address, use size, string, and dots. So we give it 0. 0 dots. Doesn't like that string. It's a string literal. If you meant to write str literal, use double quotes. Consider adding a leading B. Okay. Oh, it's looking for an array. Don't want to do array. I'm just thinking about what's a good way to do this. If I did this, where I say white display is a U8, it's 8 slots, and it's equal to 0, 0, 0, 0, 1, 1, 1, 1. Did that work? Okay, no, not quite. address white display. Not address, but borrow white display. So this is the right data type, but this is not liked. I feel like you have to do this, right? You do that, and it creates it into this, but then this doesn't like that. String. The byte string is 8 bytes long. Do I instead need to do this? Where I go 0, 0, 0, 0, 0, 0, 1. Or how about we do what? 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. Then change this to be 8. And then do the borrowing of that. Still doesn't like that. This needs to be onside. Okay. That worked. This is not at all the way I kind of wanted to do this. So I'm mostly just testing out to see what my options are. This won't be my final implementation, likely. So if I go white button is true, we want, just realize we want this to be on this line and this one to be on this line because we want it to trigger when it's white's turn. Actually, no. No, we don't. When white presses the button, we turn it to true, which means it sets it to this, which means that it turns the bottom ones to 1. We don't want that. We want it to do it the other way around. We want the black. We want the black to show instead because the ones are going to be replaced with a timer. White display. White. That's not what I wanted. Place that with 0. Okay. Alright, let's try and recompile this again. File's fine. Still not sure what's going on with that. My goodness. Look at these. Look at these symbols. Black button high. Black button high. Wait, why is it always high? Oh, these would only show when it's high. That makes sense. Okay, so that's not how to use this. It's showing. Well, it doesn't even matter which one I press. It's keeping it the exact same. So what other functions we got? Right. Raw byte. Oh, maybe that's what I want to do. Writes a single byte to the underlying display. This method is very low level. Most users will prefer to use one of the other ones. Header. The register to write the value to. Oh, that's the difference. This is where you're writing to that. Over SPI, I don't want that one actually. BCD could be right. This is where I configure the right segments on. String slice consisting of 0 to... Oh wait, no, this is what I wanted. This is exactly what I wanted. Okay, 0. And then... Hold on, what's this? This is a... Yeah, this is what I wanted. So I do, actually I can just replace this one up here. Replace this with BCD. And then do the same down here. BCD. Run it. Ooh. Okay, it's showing something. It's got a negative. That part I'm not so sure about, but it's at least swapping when I want it to. And when I press both at the same time, it just stays there. I'm all unsure why you're getting this floating one. I feel like I'm not really sure why that is. Maybe there's something off with that function. To me, that doesn't seem right. Let's go into here. Maybe because it's a negative one. What do we got here? This takes a unsigned, so that's what it expects. 1 to 9 negative ELHP, where uppercase input for alphabetic characters results in dot being sent. Length of string is always 8 bytes. Use spaces for blinking. I mean, we're clocking as fast as we can. Not too sure why this is showing it the way it is. But the key is that we got that working. Which is dope. Okay. So since we did that, I think what we can do next. I think the timer would be nice. So we'll refactor afterwards, I'm thinking. But first, let's make a string. Not a string, let's make a timer by importing the timer library. MC timer. And we're going to need to add that to our cargo toml. This is where the oscillator would have been nice. Because I'm afraid this isn't going to be super accurate. Timer. Let's go over here to embassy. And open up our time. It's called time. Version is gonna be 0.101. And what we need is the crate. Or no. We can copy this and place it underneath, but rename this to be time. And then what we need to figure out what features it has, which is in the documentation. It likely has deformat again. I think it has something to do with time, though. What's this? This crate contains the driver trait necessary for adding embassy time support. Use embassy time with already made drivers. You should depend on the embassy time crate, not this crate. You want to use what's already. If you're writing a new driver, you should depend only on this crate, not on the main embassy time crate. This will allow your driver to continue working for newer embassy time major versions without needing to update. If the driver trait has not had breaking changes. Embassy time is backed by the global time divider or driver specified at build time. Only one driver can be active in a program. Alright. I look up embassy time. Is this one used more? No way. Yeah, okay, it's not even close. Embassy time. This one might be a crate on its own. I don't think I need. I'm pretty sure I don't need to do this step down here. Looks like it's just a part of this. We're gonna get 3.0. And then let's see what features. Which would probably be in the documentation. Feature flags. It's only these two. Okay. I am going to get rid of this then. Timestamp uptime. Display timestamp with the number of seconds to start up. I could have that, but I don't want that right now. Oh shoot. Mock driver. Create a mock driver that can manually advance for testing purposes. Generic queue creates a global generic queue. Queue with 8 timers. I'd have to read into that. When using embassy timer libraries, you should not enable any generic queue features to allow end users to pick. Most tick features can be enabled. If none, it defaults to 1 megahertz. That's fine. We're fine with 1 megahertz.
Oh yeah, oh yeah. Hot in the club, in love with the dub. Active, yeah, I'm free like a dove. In love with the bass, in love with the sub, in love with the energy I get from above. Hot in the club, in
Timer. A feature that completes at a specific instant. So there's a difference between a timer that completes at an instant and our like alarm that we want to display on the screen. What we want is something that is decrementing every second. So what we can do is in our code we can make it where in our loop we enter a section that is subtracting some counter. Okay, so what if I do this? We're gonna make a mutable called white time, and this one's gonna be 16 is fine, I believe. And we're going to take it into sections. So the problem with this, let's just start with numbers. We'll just count down from numbers, and then we'll worry about the whole like 5 minutes versus 2 minutes versus 50 seconds. We'll do 500, right? $500 and 500 for black. We want to display the number directly, so I think this is where we can. Ooh, we're gonna have to do some logic. Normally, our chip thinks this is the same driver. If you were to do this in an easier way, you'd have a separate chip for just this chip, for this driver. Which I probably have, but we want to be like cost efficient. You can do some software logic to save one chip instead of having two. Plus wires as well. We need to do logic to make this countdown. Thinking about it though, what we can do is just use a number that fits only in these spots. And a number that fits only in these spots. If this is your, whether this would be your least significant, no, this is your most significant slots, right? We press the button, white finishes their turn. Yeah, we're gonna do the most significant slots up here. So what we can do is calculator out, figure out if we were to treat this as hex. No, actually, we just need to make a number that's greater than that. Thinking about it now, we can do this as a 32 instead. UN 32. 500 and then 50. Wait, hold on. This would be 1, 2, 3, 4. This would be the next one. Okay, so essentially it's this. Actually, essentially it's this even. Where one of them's counting from the top, 500,000. The other one's counting from 500. We subtract 1 from this top one. We subtract 5,000 from this, or sorry, 1,000 from this bottom one. So that way we get the number on the correct display decrementing. I just need to make sure the logic's not reversed here. So white display gets displayed whenever turn state is false. It turns false whenever you press the black button, which is this top one. You press the black button, which means that I kind of want this one to start decrementing. So this is the black display. When I press this, it enters this code state, which means it's showing white's display, which means that it thinks this is the lower bits. Right? It thinks index 1 is this, then 2 is this, 3, 4. So if I go and if I replace this statement with ooh, you know, thinking about it, treating it like the BCD might save a lot of time. It could save a lot of time. Because if you, how about we draw it out? I think this would get my ideas across better. One note. We're going to call this one timer display logic. The idea I have is we have our two displays here and here, and they have 4 positions on each, and we're already representing this entire thing as an array of symbols, essentially, right? This 8 times total. So what we can do is some logic that treats the upper half of that, so the indices 0 through 3 handles one of them, and indices 4 through 7 are handled here. You have a counter for minutes, seconds, but it's all powered off of seconds. So you can have an interrupt that triggers every second. Every second. So if you're doing just, let's say you're only doing one of these timers right now, you could have an interrupt that triggers every second and it counts, you know, or it decrements. It subtracts these two positions every second. It subtracts white time, let's say. White time. This was C. Oops. You can subtract this. And also, when white's time, we want it to trigger special logic whenever you hit that minute time. One way to do it is you have a counter that's, well, you already have a counter. You can use this white time. Whenever it is 0, 0, meaning that you're at least 100, you have a multiple of 100, then you suddenly have hit this minute time. Oh, actually, no, sorry. If we have 5 minutes, no, if we have 0 and 30 seconds, we can subtract this all the way till we get 0, 1. Let's say we're at 10 actually. And 0, 1. We subtract this a bunch of times by 1 second. We eventually get to 10, 0, 0. We want it to reset to be 9:59. So we need this counter to reset to 59. And we also need to subtract this one by 1. So if we're representing this as like a whole number, right, just a regular integer number like this, 100, let's say, we need to, no, 101. We get to 100. We basically need to do a check to see if we're modulo 100. Because when that happens, this is just going to be equal to 0. Any other number, this is going to be a false statement, right? This modulo does not equal 0. This one does. And when this one happens, we can trigger some logic where you subtract some of this here. You subtract the this position of the symbol. So that's going to be index 1. We're doing an array. Subtract index 1 by 1. If you are modulo 1000, then you will also subtract. You will subtract some logic where you subtract array 0. because now you are messing with this index, and then you can go from there. Now in the case where you got this giant, well, hold on. Yeah, white time we're going to treat as some variable. If you are 10, right? If you modulo 10, then hold on, how do I thought I could scroll this. Yeah, if you're modulo 10, you can trigger some logic for array 3, and if you're modulo 2, and if you're modulo 1, which happens every single second. Actually, you don't even need modulo. This always just happens. You subtract 1. Array 3 is always subtract 1. So the white time is what all these are checking. All these are checking white time's current value. And you can do a similar thing just with the higher ones places. So we'll start with just one side. We'll start with that because we're going to have to do something more clever when we start to work on the other alarm. Black's clock. So how does this framework work for the time in the embassy? We want a time to trigger every single X time at some instant. It's instant. An instant time based on MCU clock ticks and startup. This happens once though. I don't know if I want that. This expires at a certain time. I'm gonna change the next song. Ticker. Asynchronous stream that yields every duration indefinitely. Duration. So after 1 second, do something. It will call every second plus the time it took to previously call foo. Okay, that's not quite what I want. I do want this to always happen at 1 second. Like I want this to trigger. Error, what's this? Error turns with timeout on it. That's not what I want. Sync? What is sync? Just a trait. Duration between now and then. Not what I'm looking for either. So delay is you're out of time and you're just waiting some time. You're while looping. Duration is, are you calculating? You're giving one time and expecting an output. The other. But here's what the difference of this and delay is. Like I see that you give it 2 different inputs. Abstraction of stuff. Instant is a unit of time. Timer. Feature that completes at a specific instant. I thought it would have been this after 1 second. Right? This is still doing duration, which I think they said is a adds on top of... Oh, no. Oh, that was... Was that delay that acted that way? Delays are implemented in the best effort way, meaning that the CPU will block for at least the amount provided, but accuracy can be affected by many factors, including interrupt usage. Make sure to use a suitable tick rate for your use case. Now, I do recall in the past having been told that I could just use an interrupt the old-fashioned way rather than using this library. Trying to see my logs here. Say no async. Okay. There's my messages in this channel. Surely I didn't message him that long ago. Okay, yeah, here we go. Use hashtag interrupt from Cortex-M just like you would do in a non-embassy embedded product. I feel like I need to go into the... This is straight up library, right? If I did like hashtag interrupt like this, then I can make it trigger every second. It's like this. Yeah, it's like that. And I include it from Cortex-M, yeah. Do I even have a Cortex-M? Yeah, I do, okay. The issue is I gotta know the name of the interrupt. So let's look up. Is it microbit embedded Rust? Is that where I saw it before? Perhaps not. Yeah, none of these are gonna be using that. Non-blocking display. That's fun. Yeah, this framework doesn't have it. Maybe it was, oh, I think I remember now. It was in the embassy GitHub. Oh, actually this page might have it. That's for multitasking. What's this? Hold on. Tasking get transformed at compile time and state machines that run cooperatively requires no dynamic amount. Yep. Single stack. Yep. Obsoletes the need for traditional RTOS with kernel context switching and is faster and smaller than this one. Oh wait, what? They did a case study. That's kind of fun. Button interrupt. You have a loop. You have a delay for 100 millisecond. You're trying to see. It's just like a comparison of how they lay out the code in each language. This isn't, oh, here we go, results. Okay. What do we got here? Rust. when you use delays, your average interrupt time is much faster. Yeah, 50% faster. Dang, that's pretty good. Microseconds. I was getting 100 microseconds of error, 200 microseconds of error in my setup. So it definitely seems like this Rust is faster based on this implementation. Oh, context switching, the RTAS works. Arctic. Arctic is faster. If you keep implementing features and interrupts, then eventually you get a worse version of Arctic, so just use Arctic. Huh. Maybe Arctic is what I should be using then. What is... No, not this website. Arctic Rust. Real-time interrupt-driven concurrency. I guess that makes sense, right? If you're basing something off of interrupts, why not just use that? There's one other message. Hold on, I'm trying to find it. Give me one moment. I'm so tired of nothing. I don't know why I'm so tired. I probably just need to look to from in channel. We want it to be in Rust. Alright. From no, it's not in Rust. Embassy. Relevance, new. Here we go. Here we go. Here we go. Okay. Arctic style. Most code runs interrupts with non-real-time code, effectively called from forever loop. Arctic 2 style. Most code runs and interrupts with non-real-time code implemented as asynchronous tasks. Embassy executor style. All asynchronous tasks with different executors allow for preemption for real-time code. You can do all except for the talk one with Embassy STM32. Talk has its own type of HAL for each target. I think if I did it this way, I can just inject it in where I need it. The smallest possible Arctic applications where you just include it. That's pretty funny. Arctic, by example, hardware tasks. Uses a hardware interrupt controller. The schedule. I mean, to be fair, I'm not really using Embassy. Oh, I have this timer, but I may not even use it if I do some new way. STM32 is its own thing. These aren't part of... This is just the HAL. None of this uses the timers that they're talking about, so the interrupts that they're talking about. Can I see an example where they use interrupt? Arctic and Embassy. Embassy provides HAL and executor runtime. Arctic aims to only provide an execution framework. Embassy provides a HAL. On the other hand, Arctic provides a framework So the user is responsible for providing pack and HAL implementation. Arctic aims to provide exclusive access to resources at a low level possible, ideally guarded by some form of hardware protection. Since most Embassy and Arctic libraries are runtime agnostic, many details from one project can be used for another. For example, using Arctic monotonics and Embassy executor powered project works, and using Embassy sync through Arctic sync. Oh, though Arctic sync recommended in Arctic project works. Okay, let's go look at some examples then. STM32 Blinky. This one's probably not going to use an interrupt. That would be sick. And they don't use any embassy. Okay. They have a function called blink. They blink at... Oh, this is an asynchronous task. When is this task called? They are manually writing the register here. Know how. This is the way you do it if you're to manually write everything. Oh, but this is based off of this HAL framework. So we would just use our HAL from Embassy instead. So they created a system tick. Initialize this print thing. They print something. This is from the HAL, I want to say. RCC. Hold on. App device is this HAL pack. Peripherals. I think this pack is where the clocks is coming, or the RCC is coming from. So this is your app. You have an LED. Opal? Not sure what that's about. Task local equals LED in state. Shared local LED state false. Blink spawn. Okay, schedules the blinking task. This is the task name blink. You're gonna spawn it. Only return at okay, I'm guessing is what that is. Is everything based off of... Oh, let's see if this... Oh, is that teensy? That's cool. You can use Rust on teensy. Huh. Anyways, here is a real-time clock interrupt. Maybe we'll have better luck looking at this. See if there's a difference with the interrupts. It might be the same. This looks like it is bound to this wake up, which is that's a interrupt name. That's in the HAL. Binds external interrupt 0. Oh, here we go. You're enabling an interrupt. This is still doing it. Make interrupt source. But these functions, if I'm not mistaken, are from this framework. GPIOA, PAO. GPIOA comes from this, which just comes from GPIO, which comes from here, HAL. So this is part of their HAL still. You're still in their HAL. Huh. Okay. I'm not sure how easy that would be. This is Arctic's main page have interrupt driven concurrency. Tasks As a unit of concurrency, tasks can be triggered. Is this Arctic 2, by the way? Looks like it. Yeah, looks like it. A timer queue. Software tasks can be delayed or scheduled to continue running at some time in the future. This feature can be implemented. Oh, it can be used to implement periodic tasks. So this is what I want. A timer queue where at a specific time you trigger some task. I think that kind of thing was also check timers and their implementation. I think that was an embassy as well though. Arctic. Where was that? Is there a queue on here? Resources. Timer queue. Internally, all monotonics use timer queue, which is a priority queue with entries describing at the time at which the respective features should complete. The Arctic time framework is flexible because it can use any timer which has compare match and optionally supporting overflow interrupts for scheduling. For Arctic 2.0, we assume the user has a time library. Bug it as the basis for all time-based operations when implementing monotonic. These libraries make it much easier to quickly implement the monotonic trait, allowing the use of any timer in the system for scheduling. The trait documents requirements for each method. There are reference implementations available in this. Look great. Okay, we use SysTicks for STM or Cortex cores. So SysTick based, runs at a fixed interrupt tick rate with some overhead but simple, and provides support for larger time spans. Well, that's nice. Monotonic. Arctic time monotonic. Trait enforces proper time math between instant and duration. I see that they're using the same terminology in this as they were in Embassy on interrupt. Runs on interrupt before any timer queue handling. Deprecated since 1.2. This method is erroneous and has been disabled. Damn, okay. Arctic time. Time-related traits and structs. Prioritizing the tasks, deadlock-free execution, minimal scheduling overhead, efficient memory usage. All Cortex-M devices are fully supported, allegedly. Probably because it's not how. It's more just taking a core, which the cores, they have some very specific. Oh, it's the same website. Cores, they have specific ways of counting, and ours is SysTick. This is taking some more scheduling approach. A lot of research. I am getting tired though. I don't know if I can do this much longer tonight. Technically I'm supposed to probably stop the stream at 11:30. So I may need to do this research off stream because this might be a more larger decision I'm about to make. One thing I could probably look up is if the framework that I was following, or not framework, but the project that I was following, if it uses anything like that. This is a quadcopter that they made using Rust. They used Embassy. They used a duration from Hertz, 50 Hertz. Hold on, maybe this is the answer to our problem actually. IMU sample time. If they sampling every 50 Hertz, this could be it. IMU sample time. Where else do they use it? They use it here, where they did must spawn. Oh. They have a different task. They create a different function essentially that's attached to this sample time. Spawner must spawn. So that means they're using the where is it? Features. It could be sync, but I don't think sync. I think it's this executor. Executor, which is a way that they decide which task to jump to. But where is IMU reader? Oh, this is an external. Great. Or sorry, they put it in a different folder. IMU mod probably in here. Nope. This one? Nope. This one. IMU reader. We're looking for IMU reader. Read account, read gyro, read 6 degree freedom, account, gyro, 6 degree freedom. What's different between these two pieces of code? Nine degrees of freedom, 6 degrees of freedom IMU, 6 degrees of freedom IMU as well. I don't see anything different between these two implementations. Oh, where I2C is this? Okay, that's the same. These are the same. This is how you make your stuff more portable, but I'm not really seeing difference between at least these two. This looks like copy and paste the same code. But whatever. The point is, wait, what's functions? Hold on. Okay, the point is that we can use duration from Hertz. So 1 second. So we'll create const, right? Const time. Let's do alarm sample or tick, and we're going to do from Hertz. Or didn't we do this? We did Hertz. Hertz. It's gonna do 1. Right. Kind of yoinking from this a bit. We need to call it from the duration instead, actually. Duration from... Or they don't have a from Hertz. Embassy time. That's timer. Oh, embassy time. From... Hertz? Really? I did not like that. Also did this backwards. Wait, no, I didn't. This needs to be duration. Well, from seconds, I can just do 1. Which, that's fine. We're also going to change this to be the embassy executor, which requires a different function style. So we're going to get rid of this. And instead of declaring this as an entry, we're going to declare this as an embassy executor. Main. And this returns nothing, but it requires you to pass in 2 parameters. Something called a spawner. Actually, how about we do this? We add the crate before we type that out. Oh, funny. Let me see time. You can just do this. Embassy time. Embassy executor. And then we are looking for it's an underscore, I guess. I guess we just go to crate.io. Let's see. Executor. Is this? Yeah, this is supported, right? So 2.0. Oh, are there any flags? Ooh, that's not a lot of downloads. Cargo embassy. Hold on. I did not click on the right thing, lol. What am I doing? Embassy executor. Huh. Embassy -x executor. There we go. So 5.0 is this one. And we go to the documentation. Here are flags. Nightly. Use executor integrated embassy timer queue. Integrated timers. I think I want that. Architecture, we're gonna need that. So we're for sure gonna need some flags. So let's put this around some brackets. Features. DFMT, if that is a thing. Oops, we're missing a closing bracket. They don't say anything about it in here. So it must not be a thing. But architecture to Cortex M is definitely a thing. Executor thread. Interrupt mode executor. Maybe I want this. This executor runs tasks in interrupt mode. The interrupt handler is set up to pull tasks, and when a task is woken, the interrupt is pended from the software. This allows running tasks, async tasks, at a priority higher than thread mode. One use case is to leave thread mode free for non-async tasks. Another use case is to run multiple executors. One in thread mode for low prio, another in interrupt for high prio. High prio will preempt low prio. It's even possible to run multiple interrupt modes at different prios by sending different prios to the interrupts. Okay, you have to make an interrupt that you won't be used by software. Some chips reserve some interrupts for this purpose. sometimes named soft interrupts. If this is not the case, you may want to use an interrupt for unused peripheral. Thread is fun. This isn't quite what we're looking for. So thread is fine. Creates a new executor instance, declares an application entry for Cortex-M, spawning the corresponding function body as async task. Declare an async task that can be ran by Embassy executor. Task arena size. We'll keep this without that. Allocates tasks out of an arena. If the task arena gets too full, the program will panic. What's the pool? What is this size? If the task exists, the allocation is not released to the arena, but can be reused to spawn the task again. For multiple instance tasks, the first spawn will allocate memory for all instances. This is done for performance and increased predictability. I'm not necessarily getting this. Bump allocator. How does this get full? You're just calling it too many times? Maybe that's it? Yeah, I think that must be it. Okay, well, integrated timers. Use the executor. Integrated embassy timer queue. I think I just leave everything to default except for the architecture. And we see how it handles that. Oh yeah, first this is gonna yell at me. I don't actually have the right parameter now. We need a spawner. Spawner. Oh wait, we need to import actually. We need to import this executor. I'll do it up here. Use embassy. There we go. Executor. And then here we do a spawner. Spawner. What happens if I try to build this? Probably gonna yell at me. Build a select version for the timer driver. What if I put on nightly? Will that fix it? Nightly. Yeah, we're gonna compile this and then I'll probably in the stream because I'm getting pretty sleepy. Nightly. Nope, it doesn't like that. It's gonna give me the same error. Well, it's on crates.io. So I know it exists. Right, they got a 5.0 version nowadays. Oh, this is if you're using Nightly Rust. I'm not using Nightly Rust. I think that's what that's about. I may need to add in, though, integrated timer. One thing I can do is look at how Embassy does it on their GitHub. Does this have a link to Git? It does not. I can also look at his. Oh, where'd you put it? Oh, here it is. Look in here, see if he calls anything. Self-developed. Here's embassy. Oh, there's just a Git flag there. Did not know that. Good to know. Features. Format. Integrated timers. Executor thread. Oh, I needed to find one. Yeah, okay. Deformat he has there too. I don't know if that's needed. Executor-thread. Is that it? Executor thread. Integrated timers. Yeah, I don't know about that. Embassy time. I may need this. That's a good point. Oh. How about I get rid of time? Ooh, that was it. That was it. I was calling a version of time that was not compatible. Like I was specifying a very particular version there. Because this is going away, to me it seems like it's gonna work. Yeah. So if I just build, I don't want to run. Let's see. Okay, that's fine. We're not using interrupt anymore, so we can get rid of that. All right. Embassy time. Get rid of that. Let's get rid of. Oh, delete a little too much. Okay, let's do this again. Local variable has. Cannot find variable black display. I think I commented it out. Yeah, I did. Build this again. Dead code. Remove this mute. This can get commented out. We're not using it just quite yet. And same with the alarm. Yeah, we can keep alarm tick actually. Okay, so I hit cargo run. The same code should work. And it does. And you see? It's swapping, it's toggling. We got a chest timer. Cool. Okay. That's all. I am going to go to bed because I am sleepy. So, thanks all for sitting around and listening to me ramble while I'm falling asleep. But, we got another step with this timer. We got it to switch. We got buttons, and we got to switch which one is active, quote unquote. We need to integrate this timer, create system next time.